Welcome to the Deep Dive. We're here to unpack some really complex ideas and hopefully find those surprising insights hiding inside.
That's the plan.
And today, yeah, we are tackling one of the biggest ones in physics, gravity, its true nature. It's one of those things that once you really get it, it kind of changes how you see everything.
It really does.
Like, remember that scene in Interstellar, the planet near the black hole where
Yeah.
1 hour, there was, 7 years back on Earth?
Oh, yeah. Mind-blowing stuff.
How is that even possible? How can time be so drastically different?
Well, it sounds like sci-fi, but it's actually a real thing. It comes down to something called gravitational time dilation.
Time dilation.
Yeah, basically, time flows differently depending on how strong gravity is where you are. Closer to a massive object, time actually slows down.
Okay, so that's our mission today, to unpack why. Why does that happen?
Exactly.
We're going to look at why gravity bends light, which seems weird in itself,
Yeah.
then how that bending somehow leads to these differences in time.
And then the kicker.
And then the big one, why gravity might not be a force at all, like not in the way we usually think about it.
Right, but more like a feature of space-time itself.
So the goal is to make this make sense, intuitively, without drowning in equations.
So let's give it a shot.
Okay, so let's unpack this. To really get to the bottom of time dilation and, Einstein's view, we need a couple of foundational ideas first.
Right, the building blocks.
First up, the equivalence principle. Think about this. We've all felt it. You're in a car, maybe a train, and whoosh, it accelerates forward. You feel that push back into your seat, right?
Definitely. A very distinct feeling.
So what's the big deal about that feeling from a physics angle?
Well, what's truly fascinating, and this was Einstein's big insight, is that feeling, that push from acceleration. It's completely, utterly indistinguishable from the feeling of gravity pulling you down.
Indistinguishable.
Yeah.
Like you can't tell them apart.
Not by any physical experiment you could possibly do inside, say, a closed room. He said basically, being at rest on Earth under gravity feels exactly the same, physically, as being in a rocket accelerating smoothly out in deep space.
Wow.
Acceleration produces the same effects as gravity. It's a fundamental equivalence.
Okay, that's already messing with my head a bit. An indistinguishable experience.
Yeah.
So that's pillar number one.
Uh-huh.
And tied to that, there's the other really big one, the constant speed of light. This one always felt, just strange to me. How can light speed be the same for everyone, no matter how fast they're moving?
It is strange, but it's absolutely crucial.
What are the big takeaways from that, beyond just, the number itself?
Well, precisely because it doesn't change, it becomes this bedrock for how the universe works. It's not just some random speed limit.
Right.
It's constant, in a vacuum, always the same speed no matter who measures it or how they're moving. And because that doesn't change, other things we thought were constant, like time and space, well, they have to be more flexible.
Okay, so constant speed of light and acceleration feeling like gravity. Got it.
Yeah.
So how does this connect to light bending? Because that's where the old ideas really start to break down, right?
Exactly.
Light doesn't have mass. So Newton's gravity, which is all about mass, attracting mass, shouldn't affect it. But we see light bending around stars, around the sun. How?
Yeah, that's a fantastic question. And it's not just a thought experiment. We have proof. Back in 1919, there was this famous experiment led by Arthur Eddington.
Oh, the eclipse experiment.
That's the one. During a total solar eclipse, they looked at stars that appeared very close to the sun in the sky. And they saw that the light from those distant stars was actually bent as it passed the sun.
So the stars looked like they were in a slightly different position.
Precisely. It was real-world proof that gravity bends light, just like Einstein had predicted. It blew people's minds.
So Einstein predicted this before they saw it. How did he figure it out? How did he use that equivalence principle idea?
Well, he used one of his famous thought experiments. Imagine you're in a rocket ship way out in space, no gravity around, and the rocket starts accelerating upwards.
Okay, accelerating up.
Now you shine a beam of light straight across the rocket from one side to the other, horizontally.
Right.
But while the light is traveling across, the rocket is moving up. So by the time the light hits the other side, that side of the rocket has moved up slightly relative to where the light beam started.
Ah, so from inside the rocket, it would look like the light beam curved downwards.
Exactly. To you, inside that accelerating rocket, the path of light isn't straight anymore, it's bent.
Wait for it. Because acceleration is indistinguishable from gravity.
You got it. The equivalence principle tells us that if light appears to bend in an accelerating rocket, then it must also bend for someone standing still on Earth, feeling Earth's gravity. The physics has to be the same.
So the gravity of Earth literally makes light bend downwards, just like acceleration did in the rocket.
Yes, that's the connection. It's why Eddington seeing starlight bend wasn't just some quirky observation, it was confirmation of this deep principle.
Okay, so putting this together. Light bends near massive objects. Newton can't explain it because light has no mass. Einstein explains it using the equivalence principle. This must mean gravity is something more than just a pull between masses.
It really points towards gravity being woven into the fabric of reality in a much deeper way.
Okay, now here's the leap for me. Light bending is one thing, but how does that affect time? How do we get from vent light to, clocks ticking at different rates?
It does seem like a jump, but there's a logical path. Let's picture that beam of light again, but make it a wide beam, passing by something massive, like Earth.
Okay, a wide beam.
The part of the beam that passes closer to Earth, where gravity is stronger, follows a more curved path, right? Just establish that.
Right, it bends more.
But the part of the beam that's further away from Earth doesn't bend as much. Its path is, well, straighter? And maybe a tiny bit longer if you think about the curve. Or wait, let me rephrase. The closer path is shorter because it's taking a shortcut across the curved space.
Ah, okay, the path closer to Earth is actually shorter because of the bending.
Yes, exactly. Think of cutting a corner on a curved track. Now, here's the key. We know the speed of light is always constant for all parts of that beam.
The constant speed of light, right, our second pillar.
So if different parts of the light beam are traveling different distances, but they all travel at the same speed, what does that imply?
If speed is distance over time, and the speed is the same, but the distance is different, then the time must be different too.
Precisely. For the light traveling the shorter, more curved path closer to Earth, less time must pass compared to the light traveling the longer, straighter path further away.
So less time passes closer to the massive object. That's time dilation.
That's gravitational time dilation. Time itself passes slower in stronger gravitational fields. It's a direct consequence of the constant speed of light and the fact that gravity bends light's path.
Wow. Okay. And is there experimental proof for this time difference too, not just the light bending?
Oh, yes. A very famous one called the Pound-Rebka experiment back in 1959.
Pound-Rebka.
They basically set up detectors at the top and bottom of a tower at Harvard. Just a building, right? Not a huge distance. And they sent light signals, specifically gamma rays, which have a very precise frequency, from the bottom to the top.
Yeah.
And they measured a tiny, tiny change in the frequency of that light when it arrived at the top. Frequency is like the light's internal clock. This change, called a gravitational redshift, matched exactly what you'd predict if time was running just slightly slower at the bottom of the tower, where gravity is infinitesimally stronger.
Just in a building. They could measure that.
They could. It was incredibly precise work, but it directly confirmed time dilation.
That's incredible. And this isn't just lab stuff, right? You hear about it with GPS.
Absolutely vital for GPS. The satellites are way up there, orbiting Earth.
Weaker gravity?
Much weaker gravity than down here.
Yeah.
So their clocks actually run faster than ours on the ground.
Faster. Okay.
Yeah, by about 38 microseconds every day, combining gravitational effects and effects from their speed. It doesn't sound like much, but
But it adds up.
big time. If engineers didn't constantly correct for this time difference between the satellite clocks and ground clocks, your GPS would be off by kilometers within a single day. It just wouldn't work.
Kilometers. Wow. So this weird physics thing is actually keeping my map app accurate?
Pretty much, yeah. It's relativity in your pocket.
And it makes that interstellar scene make more sense now. That planet wasn't just near a massive object. It was near a supermassive black hole. Gargantua.
Exactly. The gravity there would be absolutely immense, off the charts.
So the time dilation effect would be huge.
Yeah.
Minutes on the planet really could be years or even decades further out.
It's an extreme example, but the physics is sound. That's what extreme gravity does to time.
Okay, this is big. Light bends, time slows down near mass, acceleration feels like gravity. So now for the real main event.
The core idea.
Yeah. If all this is true, what does it actually say about gravity itself? You hinted earlier it might not even be a force. What's going on there?
Right. This is probably the most counterintuitive part of Einstein's theory, general relativity. To really get it, we need a slightly different way to picture reality. We need to think about space-time.
Space-time. Not just space, not just time, but merged together.
Exactly. A unified, four-dimensional fabric. Physicists often use something called a space-time diagram or a Minkowski diagram to help visualize this.
Okay, what does that look like?
Well, imagine a graph. Usually the horizontal axis represents space, like your position along a line, and the vertical axis represents time.
Space and time on a graph. Okay.
And an object's journey through this space-time is called its world line.
World line.
Yeah. So if you're just standing still, not moving in space, your world line is just a straight vertical line. Only time is passing, moving you upwards on the graph.
Makes sense. Just moving through time.
If you're moving at a constant speed, your position in space changes steadily as time passes, so your world line is a straight diagonal line.
Okay.
If you're accelerating, changing speed or direction, your world line becomes a curved line on this space-time diagram.
Curved line means acceleration.
Got it. So how does this help with gravity not being a force?
Well, think back to our two people standing still on the building, one at the top, one at the bottom.
Right. They're not moving in space.
So on a flat space-time diagram, their world lines should both be perfectly straight, vertical lines right next to each other, parallel.
Yeah, seems right. They're just moving upwards through time together.
We just established that time runs slower for the person at the bottom due to time dilation.
Uh-huh. Less time passes for them. So how can their vertical world lines, representing the passage of time, have different lengths or rates if they're just two parallel vertical lines on a flat sheet of paper? It doesn't work.
Yeah, that seems like a contradiction. If they're parallel and straight, they should cover the same time distance.
Exactly. The only way to resolve this paradox, the only way for time to pass differently for two objects seemingly following straight parallel paths, is if the paper itself, the space-time diagram, isn't flat.
It's curved.
It's curved. The presence of mass and energy warps the fabric of space-time.
Whoa, okay. Like a bowling ball on a trampoline.
That's the classic analogy. The bowling ball mass creates a dip, a curve in the trampoline, space-time. Now, if you try to roll two marbles straight across that trampoline near the bowling ball,
Their paths will curve towards the dip, even if they started parallel.
right, they're just following the straightest possible path on that curved surface. And that's what Einstein said gravity is. It's not a force pulling things, it's objects following straight paths called geodesics through space-time that has been curved by mass and energy.
So the planets orbit the sun not because the sun is pulling them with a force.
But because the sun's mass curves space-time around it, and the planets are just following the straightest possible paths through that curved space-time, which happen to look like ellipses to us.
Mind blown. Okay, so let's contrast this with Newton. When I'm standing here on Earth, Newton would say,
There are two forces on you, Earth's gravity pulling you down and the force of the ground pushing you up. They balance perfectly, net force is zero, so you stay still.
seems reasonable, but Einstein says,
Nope, gravity isn't a force pulling you down. The only real force acting on you when you're standing still on Earth is the electromagnetic force from the ground pushing up on the soles of your feet.
the ground pushing up is the only force.
In this framework, yes.
But if there's only an upward force, shouldn't I be accelerating upwards? Like flying off the ground? This is where it gets really weird.
Well, according to Einstein, you are accelerating upwards.
I'm accelerating upwards right now, just standing here at 9.8 meters per second squared.
That's the assertion, yes.
Yeah.
The ground is constantly accelerating you upwards, preventing you from following your natural straight path through curved space-time, which would be towards the center of the Earth.
Okay. Is there any way to, prove that? It feels completely wrong.
There is. Your phone probably has an accelerometer in it.
Measures acceleration.
Right. If you download an accelerometer app and lay your phone flat on a table, perfectly still, what do you think it reads?
0. It's not moving.
Try it sometime. It will actually read an acceleration of about 9.8 meters solid upwards, usually shown as 9.8 because up is often negative z in sensor coordinates, but it's detecting that upward acceleration.
It reads 9.8 because the table is pushing it up.
Because the table is providing the force that causes it to accelerate upwards relative to its natural path in curved space-time. Now, what happens if you drop the phone?
It falls.
Right. It's in free fall. What does the accelerometer read then?
Oh, then it would read 0 because nothing is pushing on it. It's just falling freely.
Exactly. 0 acceleration. In Einstein's view, when the phone is falling, it's finally not being forced. It's following its natural straight path, its geodesic, through the curved space-time around Earth. It feels weightless because no forces are acting on it.
Whereas Newton would say gravity is still pulling it down even when it's falling.
Correct. For Newton, free fall still involves the force of gravity. For Einstein, free fall is the absence of force. It's inertial motion through curved space-time. The feeling of weight comes from the ground ground, pushing you out of that natural path.
Okay. This brings us back to the apple falling from the tree. Newton. Gravity pulls apple to head.
Einstein. Spacetime is curved by the Earth. The apple follows a straight path through that curved spacetime. Your head, being pushed upwards by the ground via your body, accelerates upwards and intercepts the apple's path.
My head hits the apple doesn't hit my head. Sort of.
In a manner of speaking, yes. Gravity, as a distinct pulling force, is an illusion created by the curvature.
Wow. Okay. That's the big shift. Gravity isn't a pull. It's the shape of reality itself, the manifestation of curved spacetime.
You've got it. That's the essence of general relativity's description of gravity.
So let's just recap this whole journey. We started with time running differently, like in Interstellar.
Gravitational time dilation.
Then we saw that light bends around massive objects, which Newton couldn't explain.
Explained by the equivalence principle and curved spacetime.
And these things, the bending light, the time dilation, they aren't separate weird things. They're all consequences.
They're the same underlying reality. Spacetime is curved, and the way it's curved is what we perceive and call gravity.
And the thing doing the curving is mass, or mass energy, more precisely.
Right. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. That's the famous summary by John Wheeler. Why mass curves spacetime is.
Well, that's a deeper question, still poking at the edges of physics. But that it does is undeniable, and it explains all these effects.
Okay, so before we wrap up, here's a final thought to chew on. Building on that idea of us accelerating upwards. If the ground beneath our feet is constantly accelerating us upwards at 9.8 meters solid, why isn't the Earth, expanding? Why aren't we flying further and further away from the center?
Ah, that's a fantastic question. And the answer involves diving even deeper into the mathematics and concepts of general relativity, thinking about reference frames and the global structure of spacetime. It shows there are always more layers.
Definitely something to mull over. It's not a simple picture. Not at all. But if folks want to explore this further, there are some great resources. I often recommend the book Relativity Visualized by Lewis Carroll Epstein. It uses diagrams brilliantly to explain these ideas without heavy math.
Good suggestion. And lots of great videos online, too, I'm sure.
Absolutely. Plenty to explore if your curiosity is piqued.
Yeah, the idea that time can bend, that space can curve, that gravity isn't really a force, it fundamentally changes your view of the universe. Hopefully, this deep dive gave you a glimpse into that, sparked some wonder.
It's a beautiful, if perplexing, picture of reality.
Indeed. Thanks for joining us on the deep dive.